So here I'm asked to evaluate the integral that I see, 5 plus x squared all over 9 minus x squared. So what I notice is that this is a rational function, which just means I have a polynomial on the top line and a polynomial on the bottom line. And I notice that actually the degree of these polynomials is at the same. Alright, so the highest power on the top line is 2, the highest power on the bottom line is 2 as well. So what we're going to need to do as a first step to evaluate the integral is to perform some polynomial long division. And this is so that we can get a different form of how to express this fraction, where the degree of the top line is less than the degree of the bottom line. So what I'm going to do as a first step before that is just rearrange this to make it look a bit more conventional. So I'm going to write it in terms of the highest power down to the lowest power, just to make my life a bit easier. So now I'm going to set up the long division so that I can get a different form of my fraction. So on the inside of my little division symbol, I put whatever's on the top line, so x squared plus 5. And out the front here, I put whatever I want to divide by. Alright, so what we're looking at is the highest powers that we have in both of these sections. So the highest power here is the negative x squared, and the highest power here is the x squared. So what we want is the number of times negative x squared goes into x squared. And I would suggest that the answer is negative 1 times. So if I do negative 1 multiplied by x squared, that's going to give me x squared. We've got a double negative, so it becomes positive. And then I do negative 1 times the 9, which gives me negative 9 overall. So I want to take this away from what I have up here. So x squared minus x squared leaves me with 0. And then 5 minus negative 9, so double negative makes it positive. So overall, 5 plus 9 gives me 14. So that means I have a remainder of 14 from this division. So I want to probably express this, as a fraction rather than as a remainder. So I can say it's going to be the negative 1 here, plus it's going to be the 14 remainder divided by whatever I was dividing by before. So negative x squared plus 9. Alright, so now we can see that our fraction has a lower degree on the top line compared to the bottom line. So the degree here is going to be 0 because it's just a constant. The degree here is going to be 2 from the squared. So that means that we can now actually perform our partial fraction step. And we can change this to look something again a little bit different, which helps us with the ultimately doing the integral. So let's go through and factorize this bottom line. So we've got negative x squared plus 9. Now, I put the rule up here, so recall that a plus b multiplied by a minus b is equal to a squared minus b squared. And that's something very similar looking to what we have. All right, we have a squared here, and we could express 9 as being 3 squared. So let's do that. Alright, and I'll swap it back so it looks like this, so we have the minus in the middle. So we could say it's 3 squared minus x squared. So that means a is equivalent to 3, and b would be equivalent to x when we substitute it into this other form. So let's do it. So that means we can write this as 3 plus x, I've got it as, and then 3 minus x. Alright, so if I rewrite this once more, it will be negative 1 plus 14 over 3 plus x, 3 minus x. Alright, so now let's go through and figure out this in terms of a partial fraction decomposition. Partial. Alright, part frac. Alright, so this is just the bit we're focusing on. So the 14 over 3 plus x, 3 minus x. And what we want to do is write out our dummy fraction. So we know it's going to look like a, which is a random constant, divided by the first bracket, so 3 plus x, plus b, which is another random constant, divided by the second bracket, which is 3 minus x. So we need to go through and solve for these two different constants. So I'm going to try and get a common denominator across all of my different terms here. And the common denominator is going to be what we see on the left. So I'll copy that out. So this fraction here, if I want it to have the same denominator, I'm going to need to multiply it by the 3 minus x. So I'll bracket it just to make it clear. So I need to multiply top and bottom by the same thing, because they would cancel out with each other and it'd be like multiplying by 1, which we know does nothing. So for this one here, if I want the common denominator that we see on the left, I'm going to need to multiply by the 3 plus x. Alright, so now all of our fractions have the same denominator and it's all going to cancel out with each other. So all that's left is what's on the top line, which I've written here. Now what we need to do is pick values of x and substitute those in so that we can solve for a and b, those coefficients or constants. So we know that picking convenient values helps. So if I pick x is equal to 3, what's going to happen is that we're going to get essentially a times 0. So it's going to drop out of the equation and I should be able to just get b on its own. So let's substitute that in. So 3, this is going to be minus 3, so that all goes away. And this is going to be 3 plus 3. So we're going to get 14 equals b times 6. So b on its own would be 14 divided by 6, or if you cancel the fractions down, an equivalent one would be 7 on 3. Alright, so let's pick another convenient value of x. If I pick x is equal to negative 3 here, it should knock this bracket out. So subbing in, I'm going to get a double negative here, so it's going to stay in. But this one we've got 3 minus 3, so it disappears. So we're left with 14 is equal to a times 6. So a is going to equal 14 on 6, which is the same as 7 on 3. Alright, so I'm going to jump back up here and sub in. So we've got 7 on 3 that actually ended up being both a and b, which was kind of convenient. So we could write this as 7 on 3 all over x plus 3. And 7 on 3 all over 3 minus x. Alright, so our last step is to actually try and integrate stuff. So we know we've got this that we need to integrate, and we can rewrite this in terms of these partial fractions instead. So negative 1 plus 7 on 3 x plus 3, and 7 on 3 3 minus x. So what I might do is come over here and actually integrate that expression. With respect to x. Alrighty. So the negative 1 out the front, that one's quite easy to deal with in terms of the integration. You can just use your power rule and it's going to end up just being negative x. This next one here, you can use substitution if you want to, in order to get the answer out. Same with this one here. What I might do is demonstrate this one. So what I'm going to do is let u equal the inner function, which I'm going to say is my bottom line. I then want to take the derivative of it with respect to x, and this one's actually going to come out to be negative 1 from the constant in front of the x. So if we want dx on its own, it's actually going to be negative du from rearranging that equation. So I'm going to sub all this back up into my integral. So we said that 3 minus x was equal to our inner function u, and dx is equal to negative du. So if I wanted to, I could write this a bit neater as the constant part is going to be the 7 on 3 times negative 1. So I'll leave that out the front. And we've got u on the bottom line inside our integral. So if we integrate that, the integral of 1 on u with respect to u is going to be natural log of u. And we don't want to answer in terms of u, we want to answer in terms of x, so we need to sub this back in. So we're going to get 3 minus x. Alright, so this here is the integral of this last term that we had. If you want, you can repeat the process for this middle term, go following through with this, but what you should find is that it becomes 7 on 3, whatever you have on the top line, times the natural log of whatever's on the bottom line. And because the derivative here of the bottom line is just equal to 1, it just follows that kind of pattern. For this one here, what you'll notice is that we ended up with a negative. That was because the negative came from the derivative of what was inside. It was the derivative of our inner function. Okay, so if you want, have some practice doing this integration by substitution again on that second term. And we need to put a little plus c on the end for our final answer. That's because it's an indefinite integral. We had no bounds. Alright, so that's the answer to that particular question.